All right, hello to everybody who's joining us on YouTube. Let's push on and see if we can finish the chapter today. And then we might do a little bit of revision tomorrow and maybe a little sneak peek of chapter 2 on Friday. Excuse me, chapter 2 on Friday. Um, the chapter 1 exam will be this week, and you can expect to see that in normal class times. So for section 1, that's going to be Friday morning at 11 a.m. Section 2, we'll do that at, I'll make it 7 p.m. on Thursday evening. That way people can maybe get some dinner first. So that's the beginning of lab time. And then for the hybrid section, I'll do a test at 9 p.m. on Friday night. And hopefully people have got their kids off to bed. If you're in section 1, you don't have to come for the test on the Friday morning. You could take it Thursday evening at 7 o'clock with the section 2 people. I mean, we're doing this one online, so it doesn't matter which section you join. So you'll go onto the Zoom link, which will appear, and then through there, join Connect. Yep, the times will go up. I've been kind of just seesawing back and forth this morning about what particular times to use, but I'll put that up before the end of the morning. Right, so density is the one physical property we want to look at for chapter 1. And that's about the amount of mass in a given volume of chemical, and you can attend any test you want. So the question is just popping up, distracting me here. Density is measuring the amount of matter in a given volume. Now the volume we're normally measuring is 1 milliliter, although that can change, and it's usually the mass in grams. So standard units are normally grams per milliliter for each chemical. And for each chemical in existence, there's a very distinctive value for its density at a given temperature. So if you've got an unknown chemical and you're trying to match it to a list of known chemicals, one of the things you could do would be to measure the density of that chemical and see if it matches. But just make sure you're looking at that chemical at the quoted temperature. Let me get a clean space of paper here. Basically what we have is, I need my pen here. Let's see, blue is fine. So imagine we've magnified 1 milliliter volume, and inside that space we find a certain amount of chemical moving around. Excuse me again for my horrible handwriting. That density won't change for each chemical as long as we don't change the temperature. But of course, if we increase temperature, increasing temperature means an increase in kinetic energy of matter. And increased kinetic energy means that molecules move around more. And when molecules move around more and move around faster, they take up more space. So some of these guys will have moved outside of that given volume. So at higher temperature, faster movement, maybe one of the molecules is out there, another one there, another one out here. They are no longer part of that measured volume for density. So as temperature increases, the density normally decreases because matter expands and it becomes less dense. So if you want to compare densities of different chemicals for identification, you've got to make sure you do it at the standard. That standard is normally given as 20 degrees Celsius. One sec. There we go. Sometimes it doesn't come on. So 20 degrees is normally the standard. If you don't see a temperature mentioned, it probably is a comparison at 20 degrees Celsius. Conversely, if we decrease temperature, a decrease in temperature means a decrease in the kinetic energy of matter. Basically, molecules start moving more slowly. And we talked about that with the Kelvin scale, saying that if we drop temperature cold enough, molecules stop moving. And when they stop moving, and we can't get temperature any lower. You can't drop temperature if there's no kinetic energy to be lost. And there's too many things on the screen here at once. That's my problem. Let's see, what I need is, so as temperature drops, molecules are moving more slowly. And as molecules move more slowly, they naturally take up less space. So things start to become more crowded again, more crowded than they were in that given volume of chemical. Now, of course, there's lots of chemical all around, but we just want the mass of chemical in that given space for density, because it's grams per milliliter. So it's almost as if the molecules are trying to crowd together to get out of the cold. And so with more mass in that given volume, the density, as temperature drops, density will naturally increase. Now, there are a few chemicals which occasionally do something different. A classic example of that is water close to freezing temperature, but that's the general flow. An increase in temperature means a decrease in density, and a decrease in temperature means an increase in density normally. And you'll see that thing all the time with things like a really hot day. If you look at telephone wires out in the country, those wires have probably started to droop down and get much longer as the metal expands in the heat. Okay, so it's important to have that reference point, that even though we can use density as a physical property for matter, we've got to be aware of the temperature that that measurement is made. Oh, we went way past where I'm trying to go. There we go, right, okay. So normally the comparison is at 20 degrees Celsius. And if your chemical has a different density, it's probably a different chemical. If it does have the same density, it could be a match, but it could be that there's multiple chemicals with that same density, just like you might have some people who are the same height. You could definitely discount the identity of someone if he's a different height from what you're expecting. Now, sometimes when we mix chemicals together, they don't like each other. We say that they are immiscible. And when that comes to liquids, liquids which are immiscible will separate into layers according to density. The more dense the matter, so water at 0.99 grams per milliliter, and oil only at 0.92 grams per milliliter, the oil is less dense, there's less of an effect by gravity on it, so it rises to the top compared to the water. We can start mixing other solutions together. So corn syrup is even more dense than water, a very viscous chemical. That would sink to the bottom, while the oil would be on top, of course, above the water. We could add in things like baby oil, which is even less dense, alcohol, which is even less dense than the vegetable oil. So we can make a huge big traffic light column with different chemicals. This only works if the chemicals are not miscible together. If they do like each other, they'll just form a single solution. So for example, if the density of the metal below is 7.14 grams per milliliter, what can we say about the density of the liquid saline solution? If you look at those zinc pieces, they've all sunk to the very bottom. And we said that more dense things sink to the bottom, less dense things rise to the top. And so our zinc must be heavier, more dense than the saline solution. So the one thing we could say about the saline solution, whoops. Gosh, I wish my handwriting was better. Saline solution density must be less than 7.14 grams per milliliter. That's all we can say. It's less dense than the zinc, which is a measured density of 7.14. How much less dense, we don't know. We'd have to try and find other chemicals and find a chemical which would rise to the top, which means that the saline must be heavier. And that would give us at least a range of density possible for the saline solution. Okay. Next one. So two solutions, one of them is saline and one of them glucose. And the two solutions are equal in mass, but the density of the saline solution is twice the density of the glucose solution. So which solution is which? Well, if they're equal in mass, so mass of the saline solution equal to the mass of the glucose solution. Remember, we can calculate mass using the fact that the density, that's the mass per milliliter, times the volume in milliliters would give us the total mass. So we're saying that the density of the saline is double the density of the glucose. Remember, this has got to be equal to the mass of glucose, this mass of saline. So to get the same value, and for them to still to be equal, if you've got double one parameter, the other one must be just half. So only way to get the same answer. And so that double density saline solution must be the one on the left. And the solution on the right would be the glucose solution. Double the density, it takes half the volume to create that mass of chemical. Okay, let's look at some examples. So unknown metal with a density of, let's see, 8.05 grams per milliliter, three significant figures, a mass of 65.01 grams. What would be the volume of the metal? It's often useful to start from base principles. Density is the mass divided by the volume. So we can rearrange the equation to say that volume is the mass divided by the density. So 65.01 divided by the 8.05 comes to 8.08 milliliters. Second one, density 3.29 grams per milliliter, a volume of 0.450 liters. Now our density units are grams per milliliter, so these liter units for volume have to be converted into comparable units or milliliters. So it's a factor of 1,000 between milliliters and liters. So that gives us 450 milliliters, and that would be a mass of 1,480 grams. Next one, actually the next three, take a couple of minutes and give them a try. 1.8, 1.9, and then 1.10. Take a couple of minutes. Actually, we'll make this a break because once we've gone over these, we're pretty much done for this morning. I'll finish early for a change. So take, let's see, what time is it just now? 20 past. Take 5 minutes, grab a drink or go to the restroom, and we'll come back and go over these. And we're just about finished. I will pause the video. And we're back. And I've remembered to hit the record button. So I think I hit the record button. Let me just double check that because I'm feeling paranoid. Yep, we're off and running again. Yeehaw. So let's see, 1.8. Oh, someone's trying to get in. Oh, she disappeared again. Okay, guess we're shy. Let's see. So start from base principles that density is equal to the mass divided by the volume. And let's see what data we have. We've got the density of 3.5 grams per milliliter. And we've got the volume at 0.2 liters. Now the density is still in grams per milliliter. So that volume has to be converted into milliliters by taking the value and multiplying by 1,000 milliliters to make a single liter. So that gives us 200 milliliters. And we want to know the mass. Well, mass would be the density times the volume, which gives us the 3.5 times 200. I'm pretty sure that would be 700. Yeah, 700 grams. We only worry about significant figures if the question tells you to worry about significant figures. In the Chapter 1 exam, there will be some questions which specifically ask about significant figures. So, oh, there they are. And so I try not to make every question about significant figures, although as we move on in the semester, it will become more of an issue. But as you're looking at the exam, if the question doesn't specifically say something like the appropriate number of significant figures, then you don't have to worry about that for your answer. And that should be clear from the actual answers available in the test. Okay. No other questions. We can go to 1.9. Let's see. Too many icons on my screen, confusing me. Let's see. Oops. Clear that. Back to the pencil. Right, next one. Calculating the mass of an unknown metal with a volume of 0.25 liters, a density of 8.09 grams per milliliter. So of course, base principles density is the mass divided by the volume. So if you want to work out the mass again, because that's mass is equal to the density, come on, times the volume. Volume again has to be converted into milliliters by multiplying by 1,000. So that's going to be 250 milliliters, and our density is 8.09. And the question asks for the appropriate number of significant figures, or actually asks for 3 specifically. So let's work out the answer. And I wrote that down on a bit of paper earlier. So 2,022.5 grams for the final answer. We want that answer to be just 3 significant figures. And so 1, 2, 3, which would mean the chop off point would be there. First figure for the chop would be the 2, but we can't just leave the answer as 202. That's a very different value compared to 2022.5. So when the magnitude of the number could be lost, we have to use scientific notation. So that decimal place would have to move once, twice, 3 times to make it a number between 1 and 10. So the proper answer is 2.02 times 10 to the power of 3 grams. Don't forget your units. Always look to that first number, which has to be chopped. If it's 4 or less, then we just erase and round down. If it's 5 or greater, then we round up. 15 people. Where's the... We had 19 people when we started. Some people sneaking off. Shame. Shame. Last one. 1.10. The liquid has a measured volume of 1,450 milliliters, mass of 1260 grams. Calculate the density in grams per liter and answer to the appropriate number of significant figures. Okay, no sooner said than done. So if we're looking for density this time, because that density will be mass divided by volume, We want the density in grams per litre, but volume is in N litres currently, so that has to be changed. Take the volume in milliliters and we'll divide by 1,000 to turn it into litres. That will give us 1.450. And let's see, we've got the mass of 1,260 grams. Grams, that's fine. The calculation becomes the 1,260 divided by the volume of 1.45. Just going to stick in that O again, that's 0. Although when you look at the volume initially, it's only 3 significant figures, and so the final conversion answer must be the same number of significant figures. So we can't really count the 0 this time. And our mass only has 3 significant figures too. We only count the zeros at the end if there's a decimal place, and there is not. And so our final answer should be 3 significant figures. Keep that in mind. Again, I scribbled down the raw answer earlier. That was 868.9655. And we want 3 significant figures, so there's our chop off point. First figure to be dropped is a 9, so we have to round up. So that'll be 869 grams per litre for the answer. Doing okay? Now we sometimes use density in medicine, but we're actually much more likely to start talking about specific gravity when we're looking at density in medicine. Quite simply, we're just comparing the density of some substance to the density of water. The room temperature density of water is just slightly off 1 gram per milliliter. It's actually, I think, 0.9998 grams per milliliter, but very close to 1. And so that density of the unknown compared to the density of water, if the specific gravity value is greater than 1, then that substance must have a greater density in water. And if you added to that chemical in water, assuming that they weren't miscible, that unknown substance would sink below the water level. If the specific gravity was less than 1, it means it must have a density less than water. And if it wasn't miscible with water, it would rise to the top. We use the idea of specific gravity for a couple of tests. One of the main one is looking for things like diabetes or Bright's disease in a patient. Certainly with diabetes, if you're diabetic, you're probably secreting more glucose into your urine than you should be, and that would increase the density of your urine, and it would start to give a value out with the normal parameters of 1.003 to 1.030. You'd expect urine to be more dense than normal water because there's already some waste material in the water you're passing, like urea and other waste molecules. But if glucose is being lost, then that would increase the density even further. Okay. Yay, they all cried and cheered. We are 1 chapter down, only 9 chapters to go. Chapter 2 is usually a fairly easy jaunt as well. As I said yesterday, it's really chapter 3 where it starts to get a bit tricky. So be ready and prepared, especially for chapter 3, and get ready to start pummeling me with questions when it comes to chapter 3 and others, of course. There are no silly questions. There's no such thing as asking too many questions, okay? I was always hounding my instructors if I didn't understand something. Ignoring a problem doesn't help. You wouldn't ignore a lump on your upper chest. You'd go and see the doctor and find out about it. Okay, so that is all I've got for this morning. So we'll come back tomorrow at 11, and we'll look at another practice test tomorrow on desire to learn. It'll be a separate test from the one I'm doing in lab time with the 3 sections this week, a different one, so with different problems. And then Friday morning, that'll be one of the test times. So I would say by 2 o'clock this afternoon, I will have those test times in stone up on the calendar on Desire to Learn. Okay, guys, have a good lunch. Wear your masks, wash your hands, stay safe.